On that, if PC5 sends traffic going in this direction, PC3 and 4 is going to get it, even if it's meant for PC1. Every time someone communicates on a hub, everyone gets the traffic. So this is a LAN device as well, but it doesn't work on anything. It's really a layer 1 device because we're not making any forwarding decisions. Some people call this a layer 2 device because to them it's a LAN device, therefore it's layer 2. See where that confusion comes into play? Would they be wrong saying it's a layer 2 device? Technically, yes, because a layer 2 device is something that would use the layer 2 information to make forwarding decisions. Or filtering, or, and that filtering would be either allowing or denying the data. But with a hub, I can't do that. I can't make any changes to this hub. All this hub does is allow traffic to come in and go out all the ports. So it's really a layer 1 device. Now, bridges is the concept of having this, let's say I have this bridge sitting here, and he's connected here, and then over here we'll have either another switch or a hub. And this hub here, let's say you have tons of devices. Let's say each one of these are 100 devices. PC 3, 4, 5 are each 100 devices, simulating 100. So that means we have 300 devices sitting here, and we have 400. And let's say everything was slowing down, things were getting really humongous, traffic was slowing down, and let's say we decided that we wanted to add a bridge. Now that's nice because then I could take half that traffic, because let's say we had 600 as well. I mean, PC6, which would be another 100. And we're going to move PC5 over here. So originally PC6 was sitting over here, giving us 400 addresses. I'm going to move PC5 over to here. So what I've done is I have this bridge sitting here. And what I've done is now on this side of the bridge is 200 MAC addresses. 200 PCs. Over here is 200 MAC addresses. Now, a bridge gives me the ability to say, okay, I need to speak to PC4. Well, if it's going in the hub, it's going to hit everywhere. But when it comes over to the bridge is going to say, oh yeah, PC4, I know where that's at. It's actually sitting on this part of my bridge. So when that traffic comes in and hits this bridge, the bridge will take that traffic and forward out that interface. If I had another hub sitting here, and had a couple hundred more PCs sitting over here, same thing. This bridge will have the table of all these MAC addresses. So the bridge is a layer 2 device. And he will forward that traffic based on those MAC addresses. Now, this gives the bridge a very large table. And it gives him a big job. He's sitting in the middle saying, okay, I'm going to take all this information, I'm going to record all the MAC addresses, and I'm going to be this guy in the middle. So if you ever want to talk to this section of the network, you're going to have to come through me. So if the bridge fails for whatever reason, you know what I mean? I mean, imagine that. This hub will lose connectivity to everyone. And so on and so on. You won't see, we're not going to be discussing bridges in that fashion. But I'm just giving you a definition of what they do. Repeaters is a concept of taking traffic that's coming in a interface, regenerating, making a copy of that data, and regenerating it and sending it down. We're not really regenerating. I mean, imagine voltage coming down. And let's say you start off with 5 volts. And by the time you get down here, you're like at 2 volts. You're almost dead. And you come into this device. The device says, okay, I'm going to take this data. I'm going to kill it, copy it, and then I'm going to send it on its way. And of course, when I go to resend it, I'm going to be sending it at at what any device would be sending it at, 5 volts. So this is a concept of a repeater. People like to say we're regenerating it, but really we're just copying the data. We're closing this, copying it, and sending it back down as new traffic. That's the idea of a repeater, because traffic can only go but so far before it starts losing its flow, its power, its oomph, so to speak. And of course, nodes, every one of these devices that have an IP address is a node. This is a node. That's a node. That's a node. That's a node. Make sense? And that's what all these devices are. A hub. Now, the reason why I drew that picture before was to give you an idea how they all connected. Because obviously, we're not going to have a layer 2 device sitting here on the edge of our network going into the cloud, right? I mean, it just makes no sense. It's just not going to happen. Unless the ISP offers a layer 2 solution to move your traffic. That's possible. But in our studies, we're not going to look at this ever in this fashion. Layer 3 routers sit on the edge of our networks and does routing. Anytime we're hitting a router, we're moving up to layer 3. So a hub is an interesting device here. And the reason why it's interesting, because it gives us the power to plug in multiple devices. This is way before probably you even thought about networking. When I got into IT, which was about 92, 90, maybe 94 or something like that, I used hubs. I used to go to, Computer City, and I used to buy hubs for my own personal network. And still back then, they were kind of expensive. Now, the idea was, originally when I was networking my PCs, and this is the sole purpose of playing games, this is how we had to do it. Just a cable between the two. It had to be a crossover cable. So knowing that it had to be a crossover cable and trying to figure that part out, that was really nerve-wracking for me back then. I didn't have any networking skills. I had PC skills back then, not networking. So I went out and decided that I wanted to network with just more than just one other PC. I wanted to network with my buddies. Now, eventually, I end up getting a cable splicer and creating these crossover cables going from PC 1 to PC 2. But when I wanted to network with my friends, I would create this hub. Not create it, I'm sorry, I would go out and buy this hub. This gave me the ability to communicate with other PCs using straight through cables. And this is nice. Because obviously here, as we talked about before, pin 1 and 2 was transmitting, and on the hub, pin 1 and 2 was receiving. So I did not have to deal with crossover cables. I could just plug a straight cable through. The hub took care of the rest. The problem was, every time PC 1 had to send data to PC 2, 3 would have to get it. Every time. Every time. Now, PC 3 would look at that information, open it up, and say, this is not for me, and it'll get rid of it. But that's still, PC 3 still had to involve himself. And now that we have PC 4 sitting here, he would have to start involving himself as well. Now, everything was fine until you started getting a lot of characters on the screen. Then you would start to have what we call this lag. Now, I want you to think about it. If I have 100 guys on the screen that are walking, that's fine. Especially if you're playing the game and, let's say this is Kyle and this is Tim. On Tim's screen, he hasn't explored this land yet, so it's just darkness. But as soon as my characters start to come out of the darkness, and Tim can see it on his screen, well, now all these characters in their placements and where they're at, that data has to be sent to Tim. So Tim would know where my characters are on his screen. Otherwise, what would be the purpose of networking if whatever was happening on my screen wasn't happening on his? But imagine PC2 hasn't explored this LAN yet. So he's going to be getting all this 100 characters that I'm sending over to Tim, and really technically PC2 doesn't need it yet. Now this is just theory. I'm not telling you this is how gaming works. So all the bits and all the data that needs to go to PC3 is also hitting PC2. If I need to send data directly to PC3, 2 and 4 will always get it. And this is what caused what we would call a lag. Because the PCs were slowed down, not because they couldn't keep up, but because the hub's bandwidth was just overloaded with data. And so were their network cards. So the network cards were overwhelmed. Here's another issue we had, considering the fact that everyone gets all the data. When PC1 sends the data in, and PC2 sends the data in, and if they send at the exact same time, guess what happens? There's an interesting thing that we call half duplex. Imagine a walkie-talkie. When Kyle is sitting here, he's trying to talk to Tim, and they're sitting on channel 1. This is a frequency. And when Kyle speaks into here, he pushes this button, and this allows Tim to communicate. But this channel is a pretty interesting channel because when they're communicating across this channel, once Kyle pushes that button, this channel is occupied. Occupied meaning when I'm talking on this channel, no one else can be talking, and someone else needs to be listening. Now, if Tim wasn't on this channel, if he was on channel 2, obviously he wouldn't pick up that message. But if he's on channel 1, like he's supposed to be, he will hear me talk once that voice goes down the wire, or down the channel. And Tim picks it up. When Tim does this, though, he's going to wait until Kyle finishes speaking, then he's going to push the button, and then Tim will be able to speak. And now Tim is occupying the channel, and Kyle needs to listen. What happens if they push the button at the same time? They're both trying to access and occupy the channel, and guess what? They collide. And this collision makes it so Tim can't hear Kyle, Kyle can't hear Tim, but they're both speaking, but the information isn't getting through. This is why when you use this communication, you would let the person know on the other end that you were done by using the word over. So if you wanted Tim to pull the lever, you would say, Tim, pull the lever over. And that word over, when Tim heard that, meant that he was done communicating, so now Tim can use that channel. This is called half duplex. Only one person can speak at a time, and while someone's speaking, the other person can be listening, but if they try to talk at the same time, it collides and no one hears anything. And hubs work in half duplex. And that's a problem. So that means only one PC can communicate on that hub at a time. Very interesting. If a PC can only communicate at a time, what does this mean? There's this thing called CCNA, which means carry, sense, multi-access collision detection. I'll say it again. Carry, sense, multi-access collision detection. This is an Ethernet protocol that monitors how traffic works on segments. Now, when we say segments, we mean networks, or like we had before, we had a router coming into a switch and coming into our PCs. They all on the same subnet. This is our segment here. subnet or segment. PC1 goes to communicate. He's listening on the wire. He's listening. And he's not going to try to do any transmitting unless there's nothing on the wire. And as soon as he knows that there's nothing on there being transmitted, bam, he starts sending. He starts sending his traffic, and he's good to go. Now, this is great because every PC on this segment or on this network are doing the same thing. Everyone's doing their job. They're waiting for a clear signal, and bam, then they send it out. But what happens if PC 1 and 2 both hear that clear, both listening and realize, oh, it's clear to transmit, and they both transmit it at the exact same time? Just like our walkie-talkies, they collide. Now, this is what we call a collision. When this collision happens, all the PCs on there will get this jam signal. CSMACD will send out this jam signal. And when everyone gets that jam, they're all like, okay, stop transmitting right now. Everyone stops transmitting. And then each one of them will get a random time. That random time will be milliseconds, seconds, however. So PC 1 might get 13. PC 2 will get 23. They'll all be random. And then the timer will start to click down. 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And now PC 1 will start to communicate again. And then PC 2, then 3, then 4. After theirs hit 0, they'll start transmitting. And that's the job of this, to stop that collision from happening. That's why we call it a collision detection, and we make action. We take action upon this and send out that jam signal. And this is what CSMACD does. It's an Ethernet protocol used to stop collisions when they occur. Does that mean we're going to have a collision again sometimes? Oh, most likely, yes. The chances of that happening are very high. And this hub, when you used to buy it, used to have this little light. And every time this light would turn amber, you would know something was going on. Why? Because right underneath there, guess what it said? Collisions. And you could see the collisions. It would turn amber. And you would also know something was going weird if your collision light was blinking so fast amber that it just looked like it was on. Well, I mean, obviously we're having some type of collision, some big, huge collision issues. And I've had this happen with my hubs, and come to find out it was a bad hub. I went out and bought a new hub, and everything worked fine. The hub just wasn't doing its job. So because of this is kind of an annoyance.